Now that we have a basic waveform going, how are we going to play notes with it? In this lesson, we will discover how by going over the code in the BP Basic MIDI project. But before we dive into the code, let's go ahead and load BP Basic MIDI into the BP Synth. Please refer to previous lessons on how to flash code to your microcontroller and how to connect a keyboard up for playing your BP Synth. Let's open up the ST-Link utility. Click Program Verify. Find your BP Synth code folder. Find BP Basic MIDI. Click that open. Click Open Debug. BP Basic MIDI Hex, double click. Then if your dongle is ready for flashing the microcontroller, all you need to do now is click Start, and it will flash the code to your microcontroller. Once you have the Basic MIDI project loaded into the microcontroller, you should be able to play the keyboard now. For now, all we have is a very basic sawtooth oscillator. I just wanted to show you how this acts like a monosynth. You can only play one note at a time. But you notice I'm able to hold down notes, and when I release a note, it will go back to the previous note, like this. Or 3 notes. Or I can release the middle note while I'm holding down all 3 notes, and it will know to jump back to this note. Because we're going to see in the code how we remove this note while the other note is still playing, but we have the other note still held down. The playability of the monophonic keyboard has some pretty neat features like trills. Or you can get a little bit more fancy and do something like Eddie Van Halen. That's just a basic demonstration of the Basic MIDI project that we loaded up to the microcontroller, and we will be taking a look at the code on how all this was put together to give us a way to play our synthesizer. Previously, we built a MIDI interface using an opto-isolator, a diode, and a couple resistors. But we need to connect that interface to a serial port on our microcontroller, which we mentioned is a UART port. In the first half of this lesson, we are going to focus on receiving MIDI data from the UART port and parsing the data out so we can decide what type of data it is and how our code will act on it to control our BP synth. But what is MIDI? The musical instrument digital interface was developed in the early 1980s and is a serial data interface that uses a set of digital commands to universalize digital music equipment communication. There are many informative sites that can explain more, but I will attempt to explain what you need to know for what we use in our BP synth. For the most part, when we see references to raw MIDI code, we see hex values like these: 7F, FF, 0C, 18, B1. In the code, you will be seeing hex values written as 0x7F, 0x21, 0xC7. But for efficiency, in the lessons, I'll be using a X in front of hexadecimal values so we can distinguish them from regular decimal values. For example, X10 is not the value 10 in decimal. I pronounce it as hex 10, and the decimal value of hex 10 is 16, not 10. There are many tutorials to understand hexadecimal values you can search for, but I will try to quickly give a few examples to explain them. If you can understand binary, then you can quickly understand how each hex symbol used in a hex value is representing a group of 4 bits. Hex values have 16 symbols, 0 through 9, and A for 10, B for 11, then C is 12, D is 13, E is 14, and finally F equals 15. Just like when we use more than one decimal symbol to create values beyond 0 through 9, like 10, 11, and 12, we can use more than one hex symbol to create larger values than 15, like hex 3C, hex B7, and hex 1C8B. Let's try hex 4C. In binary, it is 0, 1, 0, 0, 1, 1, 0, 0. A group of 4 bits is called a nibble, and 2 nibbles equals 1 byte, which is 8 bits. The rightmost nibble is lower in value than the leftmost nibble, so we usually call the group on the right the least significant nibble, and the one on the left the most significant nibble. So in the example, 1100 is the least significant nibble and has bit values 8 and 4 set on. So its decimal value is 12, which we use C to represent the hex value. The most significant nibble is 0100. The bit value set on in this group represents 64, but we use the hex value of 4 in this group because we only have 16 hex symbols to work with. Now what's interesting is that this is the bit group that begins with bit value 16, and if you take 4 times 16, you end up with 64. You could do it with a hex value of 2. 2 times 16 equals 32. A 2 in this 16's group of bits would be 0010. We could just call it hex 20, and the binary form of that would be 00100000. Now it's easier to see that it is the bit for the decimal value 32. What about hex 80? Let's multiply 8 times 16 and we get 128. Hex 80 in binary would be 10000000. Now we can see the bit set is decimal value 128. This is similar to decimal values where we only have 10 symbols, 0 through 9, to work with in order to make values like 100, 23, and 4,256, for example. With decimal values, we have the ones, tens, hundreds, and so on. In hexadecimal, we have groups of 4 bits, and each one can be identified by its lowest bit. So when we take a look at a full byte, the least significant nibble of that byte is the first 4 bits, and its lowest bit is a decimal value of 1. The next group's lowest bit is decimal 16. So if we were to go up to a third group of 4 bits, the lowest bit in that group would be decimal 256. So instead of ones, tens, and hundreds, in hex we have ones, 16s, 256s, and so on. Fortunately, we only need to be concerned with 1 byte of data at a time with MIDI, so we will only be using the hexadecimal 1s and 16s groups of 4-bit nibbles. Looking back to our example hex value of hex 4C, When we add the most significant nibble to the least significant nibble, we get 64 plus 12 equals 76. Let's try another example. Hex A7 in binary is 10100111. The least significant nibble is 0111 and has bit values 1, 2, and 4 set, which would equal hex 07. We get this value by adding up the decimal values of 1 plus 2 plus 4 equals 7. And since this group of bits is the ones group, we don't need to multiply anything to 7. The most significant nibble, which is a 16s group of bits, is 1010. If we treat this like the previous group of bits, we would add up the set bits, which are decimal values 8 plus 2 equals 10. The hex value of decimal 10 is A. And since this A is in the 16s groups of bits, we would multiply 10 times 16 equals 160. So the most significant nibble equals 160 in decimal. When we place the A in the most significant nibble position and the 7 in the least significant nibble position, we get hex A7. Decimal values 160 plus 7 equals 167, which is what hex A7 represents in decimal value. Hex values are strange to work with at first, but with some practice you can identify hex values in your head for 8-bit numbers without relying on a programmer's calculator to translate for you. In standard MIDI format, the hex values that start with an 8 or higher, like hex 80, hex 90, hex A0, hex B0, are command bytes. Values that start with a 7 or less, like hex 7F, hex 6F, hex 3A, are data bytes. When we want our BP synth to do something, we usually send a command byte first. Then usually a pair of data bytes immediately follows the command byte. This gives us 3 bytes total. A command byte will indicate we want a note played on or off. And we can also assign the note to different instruments. So the note could be sent on channel 1 to a synthesizer. Hex 90 would be a note on channel 1. Or we could send it to a drum machine on channel 10. Hex 99, which would be note on channel 10. By changing the least significant nibble of the command byte, we can change the channel the note it is assigned to. With the second byte, we can send note numbers. Hex 2C, hex 4F, hex 67, to let the instrument know which note number we want played. And with a third byte, we can also tell how hard we hit the key, which we call velocity. Hex 7F, which would be the maximum value, 127, would be a note struck very hard. Additionally, we can send other special commands to let the instrument know we want to pitch bend the note, control vibrato or other modulations, change the volume, and many other controls. Most of these commands will be called control changes. Pitch bend has its own special command which we will soon take a look at, but for the most part we will be using control changes to change the parameters on our BP synth. Now let's take a look at the serial port we previously set up when we configured the microcontroller in a previous lesson. Looking in BP Basic MIDI, Core, Source, Main.C, we will find UART, Handle Def Type, HUART2. This is our UART handler. If you recall in a previous lesson, the handler in this case is going to be a struct, which can be found defined in BP Basic MIDI, Drivers, HAL driver include UART.h. And when you scroll down quite a bit here, you will find the UART handle type def struct and all the parameters that are included in it. Returning to the main.c file, when we scroll down to the main function, we will find mx UART2 UART init, which if we scroll down further, we will find that function right here. Most of the code inside mx UART2 UART init is used to define parameters in the HUART2 handler struct. We can see much about how our serial port is set up from here. Most of these parameters were set when we configured the microcontroller at the very beginning using the IDE CubeMX app. We can see we are using the UART2 peripheral. Our clock speed is 31,250, which is labeled as baud rate. 31,250 is the standard speed for MIDI communication. Next is our word length, which is set to 8 bits. This means we are listening for 1 byte at a time. The rest is typical serial communication protocol that the configuration tool set as default. I will point out that there is another section of code that defines the use of our UART port. Let's back up and take a look in source HAL MSP.c. In there we find HAL UART MSP init. And in that function near the end, we see HAL NVIC set priority UART2 IRQ 00. This is the interrupt priority setting for the UART, and we see it set as 00. This means it is set at one of the highest priorities obtainable for an interrupt. When data is received at the serial port, we need to act on it as soon as possible. Back in main.c, we can see the priority we set for DMA. Look in MX DMA init, and you will see HAL NVIC set priority DMA2 stream 2 IRQ 13.0. The priority set for the DMA interrupt is set very low, which is 13. If we had set this at highest priority, it would almost never let the UART function, since the DMA is constantly streaming data and retriggering its interrupts. Let's take a look at the main function again. We see a function called while1. This is our super loop. While the black pill has power, it will constantly run anything in it over and over. We have a HAL library function inside of it. HAL UART receive IT address of HUART2 receive buff 1. What this does is it enables the UART port's interrupt. With this enabled, if the UART port gets any activity or data, it will store the data in RX buff. Then call the interrupt's callback function, which is here. HAL UART RX complete callback. Once the callback is started, we see a series of if statements. The first one is if receive buff 0 is greater than or equal to hex F0, then there's a comment, reset the interrupt for the MIDI port, and then we see that function again, HAL UART receive interrupt, and then return. As commented, this is a filter ignore any data that is F0 or greater. We do this because we have no use for any commands like those right now, so best to ignore them all. You will see we call HAL UART receive interrupt again. This function is kind of funny in that every time the UART interrupt is flagged, we have to manually re-enable it again. Relying on the call in the super loop is not adequate enough. I find it best to call it again as soon as possible. Just after that, we return to exit the UART callback so we can continue to monitor for more MIDI data. Plus, we avoid wasting time uselessly testing the other if statements. If the byte received was not a command that started with hex F, we would continue on with the UART callback's if statements. The next one is if rxbuff 0 and 0x80, MIDI rx0 equals rxbuff 0, note byte flag equals 0, HAL UART receive interrupt, return. Here we are testing for a command byte. Command bytes in MIDI language is anything that the most significant bit is set 1. Here is hex 80 in bit format. 10000000. Bytes that will pass this test in hex will be any value that starts with a hex 8, which is 10000000, hex 9, which is 10010000, hex A, 10100000, hex B, hex C, hex D, hex E, and hex F could be included here, but we eliminated it in prior code. We test for a command byte by ANDing the rxbuff0 memory value to hex 80. So if we AND hex 80 with hex A2, the microcontroller would AND them together like this. Hex 80 equals 10000000, and hex A2 equals 10100000. And after ANDing them together, we end up with the value 10000000. This is a true value since it has at least one bit set, which is the most significant bit. But if we do hex 80 and hex 7F, the microcontroller would end up with this. Hex 80 equals 1 with all the zeros, and hex 7F equals 0111111. And after we AND them together, we end up with all zeros. This is a false value since it is a 0. After ANDing, if the result is a value greater than 0, a status we call true, then we proceed with the rest of the code. MIDI rx0 equals rxbuff0. This will copy the value stored in rxbuff0 into MIDI rx0. Making a copy saves the value so rxbuff0 can be freed up to capture another value from the MIDI port. Moving on, the next bit of code we see is this. Note byte flag equals 0. We will see uses of this in a moment. It is here as a simple safety guard for possible erroneous MIDI bytes. If we are in this if statement, note byte flag should equal 0. By forcing the value to be 0 after saving a command byte, we are making sure it is 0 for the next byte that we will work on. We close this if statement with the usual re-enabling of the UART interrupt, and then the return command, so the rest of the remaining if statements are skipped. Moving on, the last if statement is if note byte flag. Since we previously made sure note byte flag is 0 after receiving a command byte, we would not continue with this if statement if we have not received the first data byte yet. So for now, we will exit it and move on to the last bit of code, which is MIDI RX1 equals RXBuff0, note byte flag equals 1, HAL UART receive interrupt. By the time we reach this group of code, we know two things. Our current data in RXBuff0 is neither equal to or greater than hex F0, nor is it equal to or greater than hex H0. So it must be equal to or less than hex 7F. Remember, in MIDI, where a byte is less than hex 80, it is either a note number, a control change number, a velocity value, or a control change data value. Control change data is sent in pairs. 071F is an example which equals control change number 7 and data value 31. Usually meaning we want to change the volume to value 31. A note data pair would look the same, 5A 7F, which is note number 90 and velocity 128. So looking back at our code, MIDI RX1 equals RXBuff0, we are simply copying the value of RXBuff0 into MIDI RX1. This is either a control change number or a MIDI note number. Now we are back to seeing our variable we ran across earlier, note byte flag. And here it says note byte flag equals 1. We are setting a flag because we are expecting the next byte received to be a control change data value or a note velocity value. This will be the second byte in our control change or note byte data pair. The rest of our code here re-enables our UART interrupt, and since this is the end of the function, we automatically return to the super loop. When the third byte arrives, we come back to if note byte flag. We should be here if we stored a control change or a note number previously. Now our note byte flag equals 1, which is a true value. So we get to continue running this if statement. The first of which is note byte flag equals 0. The first thing we want to do is reset our flag. We don't want it to remain 1 for the next time we receive any MIDI bytes. MIDI RX2 equals RXBuff0. We copy our second control change or note byte into MIDI RX2. HAL UART receive interrupt. We go ahead and re-enable our UART interrupt. Process MIDI. We now have 3 bytes, so we're going to go process them. Return. Use to exit this function and return to the super loop after we run process MIDI. We don't want to run the code past this if statement. We now have 3 bytes stored, a command byte and 2 data bytes. When we copy the last byte over to MIDI RX2 and reset the UART interrupt, we are ready to process the full MIDI message and act upon it. But before we continue with the process MIDI function, let's go over a couple interesting MIDI message behaviors. An example of what a MIDI note on message would look like is this: hex 90, hex 3F, hex 7F. This would mean note on, note number 63, velocity 127. Example of a note off message could look like either of these two: hex 80, hex 3F, hex 00, or hex 90, hex 3F, hex 00. Both mean the same thing. First is a true MIDI note off command message followed by note number and a velocity of 0. It could be a velocity of anything between 0 to 127 and it still turns off the note. The second example, hex 90 hex 3F hex 00, is a note on command message followed by note number and a velocity of 0. It's the velocity of 0 in this message that indicates a note off when using the hex 90 note on command as a note off. Another odd behavior we need to mention now is something called running status messaging. Many keyboards may use this method to send out MIDI messages. A running status message will start out with a 3-byte message like this note on message: 90, 3F, 7F. But if we strike another note while holding that one down, and nothing else like pitch bend, mod wheel, etc., we may see this right after the above message: 5A, 7F. Where's the note on byte? The controller did not send it because it knows you are sending another note on message right after the previous one. It is saving the effort of resending the command byte again. Not to worry, because our code is not affected by this. If we don't get a command byte, the code will continue to run, and after 2 more data bytes gets processed, our code will not change the previous command byte stored in MIDI RX0, but it will change the values in MIDI RX1 and 2. When we get the second data byte, the process MIDI function gets called like before. We've covered a lot so far in this lesson. This is a good place to take a small break in the lesson by ending this video, and we'll pick it back up in the next video where we will begin to run the process MIDI function.